The organometallics, your Grignard and your lithium reagents. Right? Grignard attached his name to the reaction just because we generated a carbon nucleophile, which is pretty rare to go through and do. Under both circumstances, you start with an alkyl halide and you react it with a metal, either magnesium or lithium. You could potentially do it with other metals, but those are the two more common ones. Okay? And what ends up happening is the metal will insert itself into the bond between the halogen and the organo compound. Okay? By doing so, what it has effectively done is transferred the electrons from the metal in its elemental state to the carbon atom. Okay? So our carbon atom now becomes a nucleophile. So that is an important distinction to note. We did stop here, right? This is where I should be starting. Okay. What is the charge on magnesium in our Grignard reagent? Okay. A little bit better than positive. It's a positive 2. What is the charge for the magnesium as our reactant? 0. It's neutral. Okay. For it to be neutral, it has 2 electrons. Those 2 electrons are, for at least our purposes, we can say, end up getting dumped into the bond between the magnesium and the organo compound. Because we now have a metal-nonmetal bond, it's ionic, and the electrons are effectively transferred to the carbon. So we end up with our carbon nucleophile. And we're going to look at that mechanism in a second. So we've got a lot of things or questions that come out of this. So one of the big ones is, why is it rare? Well, it's rare because it's really hard to make carbon nucleophiles. Okay, carbon cannot stabilize a negative charge very well. Very tiny and very low electronegativity. But then the question comes up then with useful. Why is it useful? I can build larger carbon structures. I can now have a carbon connect to another connect to an electrophilic carbon. I can extend the chain of my structure and get bigger and bigger molecules. So that's pretty cool. Whereas everything else we've kind of looked at doesn't get our structure bigger, it just changes the pieces that are already on it. Okay? The last one, why is it tricky? Okay? And that one's a big enough one that I'm actually going to pause. So we've got our nucleophile, which is an important reason for why it's useful. We end up having a carbon nucleophile. Why does our Grignard reaction become tricky? Because nucleophiles are very often Bronsted-Lowry bases. That is very challenging or problematic for us, which means if I'm not careful, my carbon will, instead of acting as a nucleophile, will act as a base, and now I don't have that nucleophilic carbon anymore. Okay? Take it a step further. If my Grignard reagent, okay, so if we go all the way up to our top there, if that Grignard reagent acted as a base, what would the product be? So we'd have the R group. So what we're saying is we're reacting it with H+. The electrons in that bond go to the H+, and I end up with RH. So an interesting idea in saying starting material. It's not strictly our starting material because the halogen isn't attached. What makes this even worse than going back to the starting material?
It's not reactive.
We have an alkane. We took our starting material that was reactive as a halide, then did this acid-base reaction to it that completely quenched all chemistry within that molecule, or the chemistry at that carbon. It's now back to an alkane. We've lost the ability to do any reactions. We're now backwards 2 or 3 steps from where we started. Okay. So when it comes to Grignards, we want to be very careful to minimize the presence of that acid so that we can actually use this as a carbon nucleophile. Okay? So this mechanistic step you're not responsible for. Okay? So unless you want to draw this out, you don't have to. What we are looking at is the actual formation of the Grignard reagent. The Grignard reagent is that structure on the far right. This is our Grignard. Okay. So what we're starting with is our magnesium, and you'll notice that I've drawn the 2 electrons that our magnesium has. In the course of the reaction, we end up forming this radical intermediate stage. Okay? And we have evidence to support this, which we'll talk about here in just a second. So what ends up happening? What curved arrows could we add to the top of this to help us understand?
Bromine leaving.
Okay, if the bromine leaves, what would I see happen for the ring? I would have a positive charge on that carbon. Is that what the intermediate shows? No. So this is not a heterolytic cleavage. Okay? We do not have the bromine just leave. But somehow or another, that bond needs to break and form a bond with the magnesium. So what ends up happening is we take a single electron out of the carbon-bromine bond and a single electron from the magnesium. The last remaining electron in the bond goes back to our carbon. The result is we've formed that phenyl radical and the magnesium bromide radical. We know this mechanism to be true because what happens at this stage, one of our side reactions or side products that results out of this is a compound known as biphenyl, drawn very sloppily, but it's now 2 aromatic rings connected to each other. There is no way that we can form this product unless we go through a radical mechanism. Okay? If we tried to do this heterolytically, what we'd be saying is one of those is positive, one of those is negative. We could see the existence of the negative because that is our Grignard reagent, but how do we form the positive one? Well, our halogen would have had to leave. What's the issue there? Can we form a benzene cation? No. That structure is incredibly unstable and never actually forms, which means I have to go through this radical mechanism. It's the only way that produces that product. Okay. At this stage, I now have the phenyl radical and my magnesium radical. Those can combine in a radical step known as a termination, because we lose the radical, to end with our Grignard reagent. People have varying opinions on what you want to show for this. A lot of cases you'll notice that they show the bond between the carbon and the magnesium bromide. I tend to not fall in that camp. What you will see me draw out under almost all circumstances would be the negatively charged carbon, and I would ignore the magnesium bromide. It's a bit wonky, can't officially do that, but it at least allows me to see the reactivity of the structure and I can then work within it. Okay? Questions on that? This mechanism is a radical mechanism. It is also known as a SET mechanism, S-E-T, for single electron transfer. Okay. Once we've got the Grignard reagent, we can then go through and react it in a variety of ways. Wow, that happened all at once. That should have been stepped. Okay. Before we even look at those, I want to make one more brief point out here. You'll notice that we've specified diethyl ether as our solvent. Okay. Number one, the solvent that we're going to use has to be polar. Why does the solvent need to be polar? We ended up with an ionic product. To solubilize an ionic product, we need a polar solvent. So it must be a polar solvent, hence our diethyl ether. But you will never, ever, ever see water, or in this case, an alcoholic solvent. Why is that a really bad solvent? That's polar. That should stabilize our ionic product.
It's too acidic.
It is so stabilizing, in fact, that it acts as an acid, and it does the acid-base reaction, not just a general stabilization reaction, and we neutralize the Grignard reagent by going through an acid-base step. So the solvent that we will use is almost exclusively diethyl ether. Under other circumstances, you will see any ether. So for instance, in lab, what we will end up using, which quite frankly will honestly probably fail utterly, and I'm not happy about that, we'll use THF, tetrahydrofuran. It's a cyclic ether. Okay? It's going to do the same thing to help stabilize our Grignard reagent and allow it to actually form. And once we've got it formed, then we can propagate forwards. Okay? So, in our propagating forwards, so let's erase some of those so it becomes easier to work with. What we are looking at doing is doing a nucleophilic addition. So we're going to start with our carbonyl compound or our polar pi bond, because this can happen with our imines and our nitriles as well. Our nucleophilic carbon can attack the carbonyl carbon, breaking open that pi bond. We end up forming the oxyanion intermediate. That structure is now done as far as its chemistry goes. Okay, there really isn't anything else available in solution to stabilize that negative charge, okay, which means the reaction stalls until we move to our second step. And in our second step, what we add? Acid. The acid neutralizes that negatively charged oxygen, and we end up with our alcohol. In this case, what kind of alcohol did I get? I have a primary alcohol. So to go through and make a primary alcohol, the carbonyl I had to start with was formaldehyde. It's the only way I can get a primary alcohol with a Grignard reagent. That was a lie. Whoa! It wasn't a lie. We could also potentially go through and react it with a aldehyde. Instead of formaldehyde, our subtle change is that we add an R group instead of a hydrogen. What's different about the mechanism? Absolutely nothing. An organic chemist's dream, because all I got to do is copy and paste and just change one of those letters. It's beautiful. Okay? And I get the exact same results. I get my alcohol out of this, except this time around, the alcohol is now a secondary alcohol. Okay? What happens if I now go through and start with a full-on ketone as my starting material? Exact same mechanism, no difference, but now I end up with a tertiary alcohol. So depending on the starting material, I'm going to end up with a differently substituted alcohol at the end. This is also nice because in the course of this reaction, I generate that alcohol functional group. And alcohol functional groups have all sorts of chemistry associated with them. We can now run a bunch of substitution reactions off them, turn it into alkyl halides. We could even do another Grignard reagent, okay, once we've converted it across to the halide. Okay. So all we're doing in this case is making a new carbon-carbon bond, and that carbon-carbon bond is being sourced from a Grignard reagent. The other carbon is coming from a polar pi bond. Okay? So, here's some examples. We go ahead and pick this up. We start with our ring. What we've gone through and done, or what I went through and did, was identified the polar pi bond and our nucleophilic carbon. So there's our carbon. There's our first product. We end up with the tertiary alcohol. And the next one down. Okay. We've gone through and we've followed on the patterns. We're saying, oh, everything's perfect. We get the exact same result as the last time. Except that we notice that it's not the exact same structure as the last time. There's a stupid tiny little thing on the other side. What is that stupid tiny thing on the other little side? An acidic hydrogen, which means the Grignard reagent acts as a base, deprotonates the hydrogen, followed by step 2, which protonates the hydrogen, and what we end up with, the same starting material. Okay. Couple ways that this question can be asked. Number one is just, did a reaction occur, or which of the following products? And one of the answers may be no reaction occurred. Okay. One of the answers may very well be what's drawn right here. The other one that may show up is you might see this one. And then the last one, if we want to be particularly tricky as a potential answer to show up, so this answer would be number one, wrong. Okay. But it's in there because they're getting, oh, Grignard reagent, all I got to do is put on a carbon on the carbonyl carbon, and it doesn't always work. Okay. So they may provide this one, they may do some other weird stuff, and then the last thing that you may see for what is the product of the following equation or following reaction, CH4. Okay. CH4 really is the product of this reaction. That is the only thing that actually makes sense to show as a new structure, because the other thing was the exact same thing we started with. CH4 is actually the product in this reaction. Okay. All we did was add a hydrogen to our Grignard reagent. So a variety of ways that this question can be asked and made very sneaky to make you think about drawing it incorrectly. All right, so watch out for that. Upper right-hand corner first. I went through and identified our active species, but you may realize or start to wonder what is going on with our electrophile. It helps to draw out the actual Lewis structure. What happens? Our Grignard attacks, we break the pi bond, we get the exact same result as we've been doing for every other reaction, except in this case, we form a carboxylic acid. Okay. So not only can we vary, actually I don't know why I was saying not only can we vary, because we are varying the electrophile even further in this case, from it just being a standard carbonyl to now being fully oxidized. The last two are a little bit trickier just because we've now made them not carbonyls. They're just polar pi bonds. So I'm getting tired of drawing rings. There's our phenyl, there's our carbon. Here's our new Grignard phenyl. And we'd end up with our NH as a final product. Okay. This reaction, with a very simple change, will actually go to the ketone. That chemistry we'll talk about in Chapter 18. So a simple change in the solvent can switch our product from being the imine across to the carbonyl. So watch out for the solvent, because that solvent does play an important role in the chemistry. Yeah?
The previous product that you just drew,
Mm-hmm.
it still had that polar pi bond. Could you react again?
So you may notice that there is still a polar pi bond, but before we actually put that hydrogen on there, this is the structure we're looking at. So yes, it is a polar pi bond, but is it reactive? That negative starts to stabilize that carbon. It can't formally push the electrons in there, but there's now so much electron density around that position, it's not easy to react it a second time. Okay. But what happens if we start with our now protonated structure? Now we can go through and attack. There's now not that negative charge that's preventing the Grignard from coming in and attacking, and we can go through and finalize that out. And I drew that zigzagged wrong. Okay. So yeah, we have to watch out with our intermediates in each of those cases. Sometimes the intermediate can prevent that second attack. Why might we need so long for that nitrile reaction? This one here. You'll notice that it says reflux, which means we're boiling it. and 5 hours. Why might we need those kind of harsher conditions?
Because the molecules are so big.
We've got a lot of steric concerns, and as far as the electrophilicity of that carbon goes, it's our least active one. Okay? So those are organic metallics in kind of a nutshell. So straight out of the text gave you some nice kind of figures within this when we're thinking about our Grignard reagents. They listed a whole bunch of feasible Grignard reagents. You'll notice pretty much any carbon can be turned into a Grignard reagent. So all the ones up top are phenomenal for Grignard reagents. All of those work great. When we move to the bottom, now all of a sudden they become bad. Why are the bottom ones now bad as Grignard reagents? So how about that first one, lower left-hand corner? Why is that first one a bad Grignard reagent? We have that acidic hydrogen from our alcohol, just like we did in the previous problem. So that then ends up doing an acid-base reaction. What about the next one? Ideas? It's a hint. They're kind of highlighting it. What's the problem with that carbon? It's a polar pi bond. It's not an acidic hydrogen. There's a polar pi bond within the structure. So what happens? As soon as I make the Grignard reagent, it starts reacting with itself as opposed to it reacting with the next species that we add. Okay? So that ends up being our primary issue with the rest of these reagents. Okay? The epoxide can ring open. Okay, so if I take a negative nucleophile, or my negative carbon for my Grignard, it can encounter a second of these molecules and can pop that ring open. Okay? If it's something I want, great, fine, let's do it. Most cases, that's not what you're trying to do. Okay? We're going to make the Grignard reagent and have it react with a second species outside of the reaction. Okay, so we have to be a little bit careful with our choice of Grignard reagents. Questions? Okay. Now to the fun one. I will freely admit this is one that I've taken forever to learn or remember anything about. Okay? And it's still kind of in the back of my head, like I'll try and do a synthesis, and if I can't get it to work or I see a problem, then I'll go, oh, maybe I should do a Wittig. And yeah, now it works. Okay? So it is something stuck way at the back of my head. I don't remember very much of it. It is important, though. Okay? It is a very common reaction to see pop up. So let's take a look at what's happening. We start with an alkyl halide. We've done that before. We did that with the Grignard reagent. We react that with pH3. What are the pHs? Phenols. So we are looking at a massive structure. Okay. Take it a step further, we're reacting it with phosphorus. That's in our third energy level. Okay. What happens to our electron configurations when we move up to the third energy level? This is pulling way back in the reaches of 151. The d orbitals start to become available, which means what happens when we look at Lewis structures and we try and predict shapes?
It's hard.
It becomes more difficult to deal with them. You get larger shapes. You can build more than 4 things around an individual atom. It breaks the octet rule. Why does it break the octet rule? Well, because we can promote electrons into the d orbitals. Okay? So already we should be going, oh crap, this is going to suck. Okay? That phosphorus can exceed its octet. Okay? Butyl lithium. Might be a bit tricky written out like that. So what does butyl lithium mean? Butyl is CH3, CH2, CH2. I should have picked propyl or methyl. CH2. And now lithium. What does butyl lithium give us? What was that? We could look at it as a carbon nucleophile. There's a negative charge. I don't know why I circled the lone pair. There's a negative charge on that carbon due to that metallic metal-nonmetal bond at the end. So it can potentially act as a nucleophile. What else could it act as? A base. Kind of an important distinction. A lot of the organolithium compounds tend to be used primarily as bases, not as nucleophiles. Okay? It's not a go-to rule, but if you're seeing an organolithium compound, very commonly we're using it as a base, not as a nucleophile. And then in the last step, what do we add? Our carbonyl, our polar pi bond. Okay? And in this case, it needs to be a carbonyl. What's the net result? What changed? If we look to our product, what happened? We combined those pieces and got rid of the oxygen. So effectively all we did was just delete the oxygen and then just attach that last carbon to it. Okay, without adding another carbon, which I just did. Okay? So this is going to become a tricky one. We have to be careful on counting our carbons because it's going to be very kind of tempting to do exactly what I just tried to do, is just draw that connection there. But by drawing the connection I've shown, we've now added a carbon. So you've got to be careful when you approach that. Okay? So really all that's happened is we've somehow just deleted the oxygen and attached those two pieces to each other. Okay? But this becomes a bit odd. Let's take a look at those pieces. We're taking the carbon from our carbonyl, which has what charge? Partially positive. And we're taking the carbon of our alkyl halide, which has what charge? Whoops. Huh. They're both positive. How could this reaction possibly work? Something about those first two steps is changing that positive charge from our carbonyl, or sorry, from our, what is that? Alkyl halide into a carbon nucleophile. We're somehow making that negative through the course of this reaction. That's kind of bizarre. Okay? So when we go through and try and approach this, what we want to do is look at each of the steps individually, okay, and decide what can happen. What is our nucleophile? What is our electrophile? What is our acid? What is our base? Okay? Once we've done that reaction, look at the structure. What can it do? Okay? And then after that, we go back to nucleophiles and electrophiles. So let's break it down and look at each of those steps individually. Okay. What do we see? As a hint, I'll give you the first one. We see that carbon is a partial positive from our alkyl halide. We already knew that from the previous discussion. Well, if that's partially positive, what do I need to find in the other structure? Partial negative. Where's that negative? We only have one source, the lone pair on that phosphorus. So what happens? What type of reaction would we be showing? It's a substitution. What type of mechanism? SN2. In the course of this, what happens to the phosphorus? Well, the phosphorus has now shared electrons with the carbon. It's now lost electrons. It is formally positive. Not particularly happy about that. Okay. Why would we predict this as an SN2 mechanism and not, say, as an SN1? Our substrate is primary. Okay. What would happen if I, say, made that substrate tertiary? Would I expect this reaction to work very well? No, we're now going against the grain of forming our final product. Okay? So when we're trying to do these Wittig reagents, okay, on the way to making what's known as an Ylide, or Ylide, however you want to say it, we need sterically unhindered species. The more hindered they are, the less likely that reaction is going to work well. Okay. So it's best with our primary alkyl halides. Okay. And this we can look at as almost a way of priming our carbon. We're activating the carbon for the next step of the reaction to get that carbon to hold a negative charge. Okay? So we take our species now and react it with the butyl lithium. You'll notice I've given 2 boxes. Why 2 boxes? What did we say the butyl lithium can act as? A nucleophile or a base. So predict it. And based on the length of these, I'm going to guess the top one is our nucleophile, and the bottom one, it's acting as a base. So take a minute here. Predict what your product would look like if it acted as a nucleophile and if it acted as a base. If it acts as a nucleophile, kick the leaving group off, and we now have that new structure shown where the purple bond is our new bond. Where's the activity in that structure? There isn't any. We have an alkane. Well, that kind of defeated the purpose of this whole process. So maybe it shouldn't act as a nucleophile. What happens if it acts as a base? What does the base need to do? Fix that. What did you say? It needs to deprotonate. It needs to remove a hydrogen. Okay. So where could we remove a hydrogen? We could run this under what we might predict for an elimination reaction. We could remove the hydrogen out here, and we'd end up with an alkene. Don't draw this yet. The whole point of this process was to do what to our carbon? That carbon needed to become negatively charged. Well, it is partially negative in this case, but it's not very strongly negative. Take it a step further. Couldn't I have gotten this product just by adding a base straight out of the gate with the alkyl halide? Yeah. So this defeats the purpose of what's happening with that phosphorus. So something else has to be going on here. It can't be as simple as just an elimination reaction. What hydrogen do we remove? We remove a hydrogen immediately next to our phosphonium structure. Our base comes in, pulls that hydrogen off, and our electrons now go to the carbon. The result, and I got tired of writing out all our rings, is we now have a structure known as the Ylide. What the Ylide is that we have these separated charges with the positive and negative right next to each other. Okay? So it does not have to be a carbon and phosphorus. It can be a carbon and, say, sulfur, which is a section out of your textbook. Okay? Why does this work? Because in the other case, we at least stabilize through the formation of our alkene, and we kicked out the phosphorus. This case, we don't kick out the phosphorus, and we actually make the structure even more charged. Why is this structure a reasonable structure to form? How do you stabilize the phosphorus? Give it electrons. We've now neutralized the charge on the phosphorus. But how many bonds does the phosphorus have? 5. Oh my gosh, it exceeded the octet. We can't possibly do that. But we can. We've now moved into the third row on our periodic table with our phosphorus. That phosphorus can accept the electrons from the carbon to form the alkene. Between these two structures, well, first off, what's the relationship between those two structures? Resonance. Between those two structures, which one is more correct? Okay, we might say the one on the right because we don't have any charge. The one on the left ends up being the more popular, if you will, structure. The reason being the size of the carbon is tiny. The size of the phosphorus, relatively massive. The p orbital overlap between the carbon and the phosphorus to make the pi bond is very, very limited, which means we get a very weak pi bond. The one on the right isn't super accurate for representing the reactivity of the structure as best as possible. Okay. Primary goal here is, what did we just make? A nucleophilic carbon. What can we now do with the nucleophilic carbon? Go react it with something. And in particular, because we're in this chapter, we can go react it with a carbonyl, okay, or carbon electrophile. Okay. So our resonance stabilization is what adds or allows for that formation of the Ylide, and that gets us our carbon nucleophile. We can't do this type of reaction in the past, like when we did our elimination reactions. We didn't see it because our leaving group could never accept those extra electrons. They were elements that did not have the ability that phosphorus and sulfur do. Okay? Now we enter the real fun part. We take our Ylide and we react it with a carbonyl. So now the question becomes is, how does this occur? Well, if we got a negative, why not? Let's just go through and have it attack the carbonyl carbon. Should cause that to bust open. And what would we get? Other than a giant freaking mess. How many carbons do I have? 2. Is that right? Okay. Everybody see it? Okay. Anybody see anything particularly high energy within this structure? We got a positive charge. What else do we have? Negative charge. What might be a good thing to do? Connect them. When and how they connect is up for debate. What isn't up for debate is that we form that bond. Okay? That does happen. Okay? You'll notice again that in the course of that, we end up neutralizing that charge. Okay? Again, we have a problem because that phosphorus has way more than its octet. But again, phosphorus is allowed to do that. Okay? This is where things get really wonky. Okay. Eventually, phosphorus says, this is enough. I want my electrons back. Where does it take electrons from? It has two options, carbon or oxygen. Why would it take them from the carbon? It's less electronegative. So the phosphorus can take those electrons away. But it can't fully accept them, so it takes them away by dumping them into a pi bond with the oxygen. Because oxygen, being electronegative, is sure, I'll take some of that. But then what happens to the oxygen? Careful. Too many electrons. So oxygen has to dump some electrons off somewhere. Where can it dump them? That carbon from our phosphorus bond just lost electrons. It's now positively charged. The oxygen has too many electrons, so it can dump electrons now back to that forming positive charge. The net result is that we end up forming the alkene. Okay? And we can kick off this phosphorus oxygen compound. This phosphorus oxygen compound should look familiar because what that compound really is another Ylide. Okay. It just so happens that it is a more stable Ylide than our carbon containing one. I think Ylide actually means with the carbon. Okay. The result is we now have our alkene at the end of our Wittig reagent. Any issues that you see that might be popping up with that alkene? We haven't talked about these in a while. We have a cis-trans issue. Okay. Which product should form? Trans is lower in energy, okay, but do we always form the trans? No, sometimes we get the cis. It depends on the stereochemistry of what's happening in that magic little transition state in the middle. Okay? And that becomes kind of a mess to deal with. What you guys end up getting responsible for, or being held responsible for, is that we get a mixture of cis and trans isomers out of this. Okay? What you are primarily responsible for is that we formed that alkene. We have the alkene now. Don't worry about the cis-trans isomers. That said, there are some patterns that fall out of this. Oops. Oh. Shoot. Well, I don't have it memorized, so I can't add that extra information. Dang it. The E and Z isomers become dependent on the electron withdrawing or donating effects of the groups around your double bond, the forming double bond. So if we change those from electron donating to electron withdrawing groups, we see a switch in favoring of the cis or trans isomers. Okay. Kind of neat. It's a mechanism that is entirely up for debate. If you guys want to learn more about it, you can feel free to go on the internet and see what's going on with it. But it is kind of cool. Big deal. We get the alkene, and we've expanded our carbon structure. Two big conclusions out of the Wittig reagent, or Wittig reaction. So here are some Wittig questions. See what you guys can come up with. We do our substitution. There's our pH 3 with a positive charge. The second step of that reaction removes a hydrogen from the carbon where our phosphorus is attached, which makes that carbon now negatively charged. Okay. There's our carbon nucleophile. That structure has a nifty little resonance structure, which should look really familiar, because that, for all intents and purposes, is the reagent in the second question. So in the second question, we just cut out all the individual steps and immediately gave you the reactive species. First question still had an extra wrinkle there. You had to be able to convert your line angle into the actual ketone structure. The nucleophile attacks your carbonyl. You'd have your O-. Okay. This is where you have that four-membered ring, which looks really ugly. Okay. So what you might do within this, see if I can do this. This right here, left side, those are your carbons. Right side, oxygen, phosphorus. So in the drawing that we've got here, we've flattened it out. Those are all now on the same plane. Bring them up. Here's the oxygen, here's the phosphorus coming out of the plane at you. Here are your carbons in back. What do? This so bad. There goes our phosphorus and our oxygen. Here are our carbons left behind. So all we've done is now erased the oxygen and phosphorus off of our structure because we've removed them. But at the same time that we remove them, we also have to form the alkene. Kind of, sort of. The next one, I did this particularly obnoxious because I drew it in a non-left to right fashion, which I will then have to switch to left to right. We can just delete the oxygen and put the carbon in place. We can jump straight to our answer. Okay, we don't have to go through any kind of weird intermediates if we don't want to. Last one, that ends up being the alkene that we're forming through our Wittig reagent. We can get two different options. Let's see if I can actually do these. So there's one part, and then the other part would be 3 carbons and our bromine. We then run through our 1, 2, and then bring in the carbonyl. The other option would be to split it the other direction. Right? 1, 2, 3, 1, 2, 3. So it looks like I counted the carbons right. Which of those two methods would work better, blue or red? Blue, because it's a primary alkyl halide that's going to react better with our phosphorus triphenylphosphine, sorry. The triphenyl phosphorus structure, or
so
PPH3.
would those two be the differences between the kinetic and thermal?
Ooh, I have not even considered looking at kinetic and thermodynamics for this, so I have no idea how to answer that question. I'll have to get back to you on that. I would probably, as a first run, say you don't want to look at that. But I'll see what I can come up with in lab. See if we can't come up with a good explanation there. Questions? Okay. So this just happened to be another version of the mechanism that was presented through a different textbook, hence the copyright at the bottom. Just going through to form the Ylide. They had nice curved arrows. I thought it was pretty, so I guess I left it in there. That's about it. Okay. Questions on it? Good. Retrosynthesis. Okay. What we're trying to do is recognize the starting material we've got and come up with ways to make that new bond. Okay. So we have an alkene here. So we just learned a method that would allow us to do this through the Wittig reagent. But do we know how to make alkenes in other ways? We could try and do an elimination. Right? So what we could do is to redraw that structure and put on a halogen. Now when I add base, I can go through and do my elimination to make my product. What's the problem? How many elimination reactions are possible? 3 of them. I could remove a hydrogen out here, I could remove a hydrogen there, or I could move a hydrogen in there, assuming that green one shows up. The purple one we might ignore because least substituted. Okay? Not going to be particularly likely to go through and make that one. But what about the blue and the green? They both form highly substituted alkenes. So if I put the halogen there, I get 2 products. Goes to either position. Well, that means a crappy yield. If I did it with the Wittig reagent, how many products do I get? Just the 1. So the Wittig reagent would be a better choice than going through and doing the elimination. The other option, just in case some of you are saying, well, you didn't have to put the bromine there. Thank you. You're right. I did not. We could have put it in here. We're still going to run into a similar situation. It's a little bit better for us. We still have 3 possible locations that we could eliminate from. The blue one would be the best, because that one would be the more substituted double bond. But the green and the red are tri-substituted. We're going to get a lot of products coming out of this. That's going to be a pretty crappy yield. So when we go through to make an alkene, it can make sense to go through and use a Wittig reagent instead of a standard elimination reaction, because the standard elimination can result in lots of different products. Okay? Questions on that? Good. Starting, what is today?
Monday.
Monday? Is it really only Monday?
Yeah.
Oh. Well, Wednesday, guess what? Your quiz is going to be, what are the 2 retrosyntheses that you could use to make this product? Since you guys didn't ask, you don't get that answer. And it'll be 2 methods to go through and do that reaction. Why not worry about the ones through red? Well, I wasn't paying attention when I put them into the slides. The first one is officially chapter 19. The second one is officially chapter 18. And the fourth one requires a mechanism that you don't know yet, technically, that we'll talk about in chapter 20 or 21. So the first 2, by exam 2, you'll know how to do those first 2. Okay? So quiz Wednesday, this question, and 2 methods to go through and make this. That'll be your quiz. Okay? Cool, so I'm doing pretty well as far as time goes. Your textbook references something known as the sulfonium Ylides. You'll notice that it is very similar to the phosphonium Ylides that we just did with the Wittig reagent. We take a sulfur compound, we react it with methyl iodide, a good electrophile, which generates this a positively charged sulfur, which we can stabilize by removing a hydrogen from one of the methyl groups to form our sulfonium Ylide. What is now special about this reagent is it can react with polar pi bonds as well, and it can come up with another way to make epoxides. Kind of neat and nifty. The only reason I'm mentioning it is that if you move into biochemistry, there is a sulfur compound, and I really wish I'd spent the time to find it, but I couldn't remember what it was off the top of my head, that transfers methyl groups in a very similar fashion. Okay? So this type of reagent is used in biochemistry. Okay? In our natural, everyday biological processes, this is happening every day. Okay? So it's just kind of a neat reaction to mention. Because of that, you're doing the same kind of chemistry through it. It reacts with a polar pi bond, and then you get the epoxide out of it. So kind of neat, does some weird, goofy stuff. There's a question in the homework on it, and that's about it. Okay? I don't think I will write a question on this on the exam. Okay? So I just want to at least mention it's there. Read it. Kind of neat because it does some cool stuff, and that's about it. Okay? Questions? Yippee-ki-yay. Spider diagram. Almost completely done with chapter 17. The only thing left to talk about is really this extra reagent here known as the Gilman reagent. Right? All that's happening is that we are now taking our carbonyl compound and we are conjugating it with an alkene. And as we talked about whenever ago, probably last Monday, that conjugation means that we have two sites of electrophilic characteristics. The carbonyl carbon is now extremely electrophilic because it is attached to an electronegative oxygen, making that carbon quite partially positive. However, or in addition to, I have conjugation with the alkene, which can now do resonance, which means that that blue carbon is now also partially positive. Which one is more positive? As a hint, I didn't do a very good job drawing it, so let me fix that a little bit. Which one is more positive? Why is the carbonyl carbon more positive?
Because it's attached to more electronegative.
It is directly attached to an electronegative element. So that carbon becomes the larger positive charge. So if we now introduce a nucleophile, we might predict it to go for the most positive atom, and we would expect our products on the left. We got our standard nucleophilic addition reactions. Okay. However, as we go through and run our reactions, someone started to note that when we changed the strength of the nucleophile and made it slightly less strong, the nucleophile stopped attacking the most positive carbon. And it instead attacked the other, oh, thankfully I switched the orientation on that. I apologize. Okay. It attacked the other carbon. That's a bit odd. Why would it all of a sudden switch which carbon it attacks? Because we look at our starting material and we say that is the most positive carbon. Right? This is where that lecture on kinetic versus thermodynamic can come into play. Because if we go through and compare these two structures, in one case we have effectively an alkene and an alcohol, and in the other case we have a ketone. So we are comparing a ketone to an enol. Which is favored? The ketone, and it is favored because it is the thermodynamic product. What we are getting out of this reaction is a kinetic versus thermodynamic system on how those things are reacting with each other. In my opinion, it is very tricky because what you are shifting from is something that we would still specify as a strong nucleophile. If we look at the Gilman reagent, what it generates is a carbon nucleophile. However, the rest of the Gilman reagent stabilizes the carbon nucleophile to the point that it now is just a strong nucleophile, not a stupidly strong nucleophile. And we're looking at a very thin gray line that tells us the difference between which product we get. What you will be responsible for is just knowing that line. If you're on the left side of it with the strongest nucleophiles, you're looking at chapter 17. If you're on the right-hand side of it, mostly chapter 18, the Gilman reagent, which officially shows up in chapter 17, you're also responsible for. Okay? So you've got that conjugation. It's ultimately what we just broke down right here. I really want to keep talking about this because I think it's neat, but I need to